So, thank you all to the organizers for having me here today to talk about intrinsic potential models and applications.
So, intrinsic potential describes the capacity of streams to provide high-quality habitat. Coarse scale stream attributes that are persistent, such as valley constraint, mean annual flow, and channel gradient, shape fine scale transient habitat features that the fish select for, but that aren't as readily mapped from digital elevation and climate data over large areas. Intrinsic potential has a species-specific interpretation. So, for example, high gradient constrained reaches of stream have a high intrinsic potential to provide the types of habitats preferred by steelhead, whereas low gradient unconstrained reaches of stream have a high intrinsic potential to provide the types of habitats preferred by coho salmon. The actual condition of stream habitat is a function of intrinsic potential, or this static geomorphic template. Natural processes that deliver, transport, store wood, sediment, and water. And in most places, human uses such as forestry and agriculture that interact with these natural processes and this static template to determine the actual conditions of stream habitat. In the modeling that we've been doing, the approach starts with delineating a stream network and stream attributes such as the gradient and valley constraint from digital elevation models. Then evaluating the stream attributes using field data, and then indexing these attributes on a 0-1 scale based on their presumed value of habitat for a given species. And I'll talk about this in a little bit more detail in just a second. And then finally calculating the intrinsic potential from these index scores. Now, in some cases, folks have gone on to evaluate the sensitivity of model outputs to inputs, and then evaluating model outputs relative to real field data to get an idea of the dependability of model outputs. So dropping back to that indexing process, the index value assigned here using gradient as an example ranges from 0 to 1. For steelhead, the maximum index value of gradient is assigned at gradients between 2 and 3% with no use assumed at gradients in excess of 10%. For coho salmon, in contrast, the maximum index value of gradient is assigned to the minimum values of gradient, and then no use is assumed at channel gradients in excess of 7%. Then the intrinsic potential is calculated for the Oregon coastal province, for example, by taking the indexed values for each of the attributes for flow, gradient, and valley constraint as interpreted for steelhead and for coho salmon, taking the geometric mean of those attributes. When the model for coho salmon was applied in California, the one that had been developed in the Oregon coastal province, it was clear that there were some areas that that we were modeling as having a high intrinsic potential where the fish never occurred historically due to naturally high water temperatures. So in an effort to evaluate this, the upper known distribution of coho salmon was mapped relative to mean August air temperature. And as you can see here for the Russian River Basin in California, that where mean August air temperatures exceeded 21.5 degrees C, coho salmon did not use these areas. So we could take that mean August air temperature as a mask and basically just turn off the intrinsic potential, use it as a binary switch wherever that threshold was exceeded. So although the temperature wasn't incorporated necessarily into the model itself, that consideration was brought into the modeling. So intrinsic potential models have been developed for a variety of salmon species and applied from Alaska all the way down in coastal areas into California. This is just an example of the intrinsic potential models for steelhead and coho salmon, mapped over 96,000 kilometers of stream in the Oregon coastal province. The distribution of intrinsic potential, high intrinsic potential, differs between these two species. You can see for steelhead, the areas in the dark blue tend to be located in montane areas that are further inland, whereas the high intrinsic potential reaches for coho salmon tend to be in lower areas of lower topographic relief that drain directly into the Pacific Ocean or into the Columbia River. Now, this same pattern is evidenced when the data are summarized by basins. Again, the areas in the darkest blue having the highest length-weighted average intrinsic potential. So, as I mentioned, the sensitivity of model outputs to inputs have been assessed and using a variety of techniques. For the Oregon coastal province, for steelhead and coho salmon, we used a Fourier amplitude sensitivity test in the SimLab software to evaluate the sensitivity of the model inputs to outputs. And we found that for all three of the sub-provinces where we looked in the Oregon coastal province, that the models were most sensitive to channel gradient and least sensitive to valley constraint. Similarly, a variety of techniques have been used to evaluate model outputs relative to real field data. For example, in the lower Columbia River, Chinook salmon model was evaluated by applying the model for all reaches across the landscape, and then looking at how the reaches that had been identified in the field by the Washington Department and Oregon Department of Fish and Wildlife, those reaches that had been identified as spawning reaches, how the distribution of intrinsic potential values differed from just the general overall reaches in the landscape. And you can see that those spawning reaches tend to occur in areas that were modeled as high or very high intrinsic potential, suggesting that the model is performing as one would hope. Another example of how intrinsic potential models have been evaluated is demonstrated here with coho salmon for the Oregon coastal province. When you look at the intrinsic potential here on the x-axis, you can see that as intrinsic potential increases, the probability of observing coho salmon increases, and the probability of not observing them or finding them absent decreases. So this multinomial logistic regression model was able, just based on intrinsic potential, to distinguish between reaches where fish were present and those in which they were absent. However, it didn't do a very good job at distinguishing between the low and the high density class. Adding the dominant land use class to the model, as well as an interaction term between intrinsic potential and the dominant land use class, improved model performance and suggested that the relationship between intrinsic potential and juvenile coho density class was a function of land ownership. So for the public lands, the State Forest Service and BLM, you can see that the probability of a reach being in the high density class, as shown here in green, increases with values of intrinsic potential. That was not the case for the private ownerships. The probability of being in the high density class was relatively insensitive to the values of intrinsic potential, and basically just a horizontal line with the intercept being at a higher level for private industrial than private non-industrial lands. So the intrinsic potential models, once they're developed, they've been applied in a variety of ways. One of these is looking at the land uses, the land ownerships, and the land covers adjacent to these high intrinsic potential reaches. So as you see here, illustrated for steelhead and coho salmon in the Oregon coastal province, that the forestry activities are the dominant land use adjacent to the high intrinsic potential reaches. For coho salmon, a greater percentage of the area than for steelhead is in more developed uses of ag and urban. Now, looking at land use projections that were undertaken as part of the coastal landscape analysis and modeling study, this isn't projected, differences in land uses aren't projected into the future, and the situation remains basically the same. So if habitat and populations of these species are going to be conserved, it's going to require targeting activities for protection and restoration on all ownership or all land use classes, including forestry, and then the more developed uses as well. Another way in which the models have been used is estimating historical fish production. So intrinsic potential was used to estimate the number of adults returning to basins, and this was done as part of the technical recovery team efforts for coastal coho salmon. And then the adults from historical cannery records were also estimated, and then a relationship was developed between these two, allowing one to predict the historical abundance in basins lacking these historical cannery records, just using the intrinsic potential values and a variety of assumptions based on ocean conditions and habitat width and a variety of other assumptions. So similarly, the intrinsic potential model outputs were related to the outputs from the ecosystem diagnosis and treatment model, and this much more complex model has only been applied in relatively few areas, so the intrinsic potential could be used as a surrogate for habitat capacity where this more complex model has not been applied. The maps of intrinsic potential can be used in prioritizing in-channel restoration, as has been done for culvert repair and replacement. Eric Anderson used the intrinsic potential outputs in the Cascades, and I know the Siuslaw National Forest has used the intrinsic potential model outputs for identifying those high-value culvert repair and replacement areas. Intrinsic potential can also be used in addressing the effects of historical splash damming, so identifying those areas where splash damming and log driving occurred that are in high intrinsic potential areas. And the mapping was done for Western Oregon for splash dams and log drives recently by Becky Miller for her master's thesis. As Dan Miller talked about, intrinsic potential can be overlain with areas having a high probability of being affected by a debris flow, and where you see this overlap between areas that are likely to initiate and deliver debris flow materials to high intrinsic potential reaches, then one can look upstream and upslope and focus conservation, restoration on the forested areas above these high intrinsic potential reaches to provide for sources of large wood. So if intrinsic potential is going to be used in any sort of conservation prioritization, it's important to step back and look at the overarching aquatic conservation goals in the context of our currently degraded riverscapes. So if one is interested in targeting areas of high intrinsic potential and currently good conditions, focusing both in the short term and the long term on protecting habitats and populations, this from an overarching perspective would be a wise investment. In contrast, looking at areas that have high intrinsic potential but are currently in poor condition, the focus there over the long term is likely going to be on restoring ecological conditions and processes. However, that may take a back seat to immediately focusing on, in the short and midterm, protecting habitats and populations wherever conditions are good, given the current situation we find ourselves in, regardless of the value of high intrinsic potential. So anywhere conditions are good, that may be an area to focus on short-term protection and of habitats and populations, looking to the long term maybe for some more flexibility as these areas are secured, providing the opportunity for colonization as these areas are recovered. So with that, I'll just say thank you, leave you with a few resources, and acknowledge our funding sources. So thanks a lot, and if you have questions, I've got 1 minute. So. Perfect.